Electrostatics 4. In this chapter, we would learn number 1 behavior of conductor in electrostatic field, number 2 electrical capacitance, number 3 principle of capacitance, number 4 capacitance of a parallel plate capacitor, number 5 series and parallel combination of capacitors, number 6 energy stored in a capacitor and energy density, number 7 energy stored in series and parallel combination of capacitors, number 8 loss of energy on sharing charges between the two capacitors, number 9 polar and non-polar molecules, number 10 polarization of a dielectric, number 11 polarization vector and dielectric strength, number 12 parallel plate capacitor with a dielectric slab, and number 13 Venn diagram generator. The learning objectives for today's topic are to understand the behavior of a conductor in a uniform electric field and the concept of electrical capacitance. Behavior of conductor in uniform electric field. Number 1. Net electric field inside a conductor under electrostatic conditions is always zero. When a conductor is placed inside an electric field E0, there is flow of electrons inside the conductor, so that an electric field known as induced electric field EP is set up inside the conductor in a direction opposite to the external electric field E0, such that the net electric field becomes E is equal to E0 minus EP. As the flow continues, EP goes on increasing till it becomes equal to E0, and hence net electric field inside the conductor becomes zero. This is known as electrostatic conditions. Therefore, under electrostatic conditions, there is no net electric field inside the conductor. Number 2, the electric field just outside the surface of conductor is perpendicular to the surface of conductor. When charge is given to a conductor, the charges flow along the surface and rearrange themselves till the net force on each charge is zero. This is called electrostatic condition. After that, there would be no flow of charge along the surface. Let the electric field E is making an angle theta with the surface. Then the component of electric field along the surface would be E cos theta. As electrostatic condition is reached, therefore E cos theta is 0. But E is not 0, therefore cos theta is 0 or theta is 90 degree. That is, electric field intensity E is always perpendicular to the surface of conductor. 3. Net charge in the interior of a conductor is 0. The charges are temporarily separated. The total charge of a system is 0. So as flux phi is equal to E dot ds surface integral is equal to Q by epsilon naught. Since E is equal to 0 in the interior of the conductor, therefore Q is equal to 0. That is, net charge inside the conductor is always 0. Number 4. Charge always resides on the outer surface of the conductor. Suppose a conductor is given some excess charge Q. Construct a gush surface just inside the conductor. Since E is equal to 0 in the interior of the conductor, and therefore Q is equal to 0 inside the conductor, and hence whenever the charge is given to the conductor, it comes on its outer surface. Number 5. The electric potential is always constant for the entire conductor. On the surface of conductor, there is no electric field component along the surface of the conductor. Therefore, no work is done in moving a charge on the surface of conductor. Therefore, electric potential at every point on the surface of conductor is always constant. Also, dV is equal to minus E dot dr. Since E is equal to 0 in the interior of the conductor, therefore dV is equal to 0, that is V is equal to constant. Hence, electric potential inside and on the surface of a conductor is always constant. Number 6. Surface charge distribution may be different at different points on the surface of conductor. It is positive at the points where the positive charge is present and is negative for negative charges. Also, surface charge density sigma is equal to q charge over surface area S, where S is 4 pi r square. R is the radius of curvature of the surface. Larger the radius of curvature, smaller is the surface charge density, and hence where the radius of curvature is less, surface charge density is more, and vice versa. That is why pointed ends and sharp edges have more surface charge density. Every conductor is an equipotential volume, three-dimensional, rather than just a equipotential surface means two-dimensional. Next is electrical capacitance. The ability of a conductor to store charge is known as its capacity or capacitance. When charge is given to a conductor, it raises its potential. More the charge given to the conductor, more is the potential. That is, the potential of a conductor V is directly proportional to the charge Q present on it. Or Q is proportional to V, or Q is equal to CV, or C is equal to Q by V, where C is constant of proportionality known as capacity of the conductor. If V is equal to 1, then C is equal to Q. Therefore, the capacity or the capacitance of a conductor is defined as the charge required to raise its potential through one unit. SI unit of capacitance is farad. Capital F is the symbol for the unit and the symbol for capacitance is as shown. Capacitance is said to be 1 farad when 1 coulomb of charge raises the potential of the conductor by 1 volt. Since 1 coulomb is a big amount of charge, the capacitance will be usually in the range of millifarad, microfarad, nanofarad and picofarad. The capacitance of the conductor depends upon number 1 shape and size of the conductor and number 2 nature of the medium surrounding the conductor.